Okay, so in this lecture, we are going to introduce the shortest path problem. Okay, so what is the shortest path problem and why is it important? All right, so what's the shortest path problem? So you can guess what it is. You are given a weighted directed graph. Okay, let's put some cycles in there, no problems. So you're given a graph and the graph has weights on the edges. It can even be negative weights. All right, so it has weights on the edges, and suppose I have a source and I have a destination. Okay, so you ask the question, what is least weight path from the source S to the destination T? Okay, so you want to know what's the path of least weight and what's the weight of a path. So suppose I go directly from S to T. Suppose I go directly from S to T. The weight of this path would be the weight of the edge S to T, which is 1. Now suppose I go from S to A to B, B to T. Then the weight of this path is 2 plus 3 plus 1, which is 6. Suppose I go from S to B and B to T. The weight of that path would be 2.5 plus 1, 3.5. All right. So, all right. So what about the negative edge here? So maybe I can go from S to A to B, B to T, T to A to B, B to T. But that makes no sense because if I take this cycle here, 3 plus 1 minus 3.5, if I take this cycle here, then this cycle is going to have an extra weight of 0.5. So it makes no sense to take cycles. All right. And we will see this formally in a second. All right, so the least weight path from a source to a destination. And this is a very important problem. Every time you log on to Google Maps, you are entering a source address from, you are entering a to address, and you get a route to go from your address, your from address to your to address. So that's an instance of the shortest path problem, right? Now, the interesting thing about that is what are the weights in your graph, right? What are the weights? The weights can be travel times. The weights can also depend on congestion, how much traffic is there, all right? The weights can also depend on the distance. Even though travel time is correlated in a positive sense with distance, it doesn't necessarily mean that as the distance increases, travel time also increases monotonically. Sometimes the distance can increase and the travel time can decrease because you're traveling on a faster highway with faster speed limits, with higher speed limits, right? So it depends really. And Google gives you the option. It gives you the option to sort, right? Google gives you the option to choose distance or choose travel time, right? So it's an interesting way, and it's actually more sophisticated, way more sophisticated than the shortest path problems that we are going to study in this class. But what we are going to study in this class forms the foundation for understanding everything else, so it's going to be important. All right, where else are shortest path problems solved? Well, in a lot of other places as well. So shortest path problems are solved by companies like FedEx or UPS, who are doing logistics, like travel websites for planning airline routes. Right? So shortest path problem is not just solved by Google, it's being solved in a lot of places. And there are many problems which do not have anything to do with graphs, which do not have anything to do with shortest paths per se, but knowing shortest paths, you can solve them using shortest path. Like for example, playing Pac-Man, playing games like Pac-Man. If you ever played the Pac-Man game, you have a bunch of evil characters. You have a bunch of evil characters that are trying to eat your good character, okay? And your good character is trying to eat some candy through a maze, and the evil characters are trying to chase after you. Well, the evil characters are basically going to be controlled by some form of a shortest path algorithm. Okay, if you have played, this is a classic computer game. For those of you who were not around in the days of classic arcade games, this is a classic game. Very good. So at least I've given you the impression that shortest path is important. If Google Maps were not important enough, then you know that companies like FedEx, UPS, travel websites, a lot of companies rely on shortest paths. Okay, even networking companies, where during routing, I want to know the shortest path from A to B. All right. So shortest paths are important. All right. Let's now talk about shortest path problems, a hierarchy of shortest path problems. In general, we will study two flavors of shortest path problems, single source and all pairs. So what do they mean? So in a single source shortest path problem, you are given a graph. Okay, you're given a directed, weighted, directed graph. All right. If you're given a weighted directed graph and you're given a single source S, you're given a source vertex. Now give me the shortest paths from S to all destinations. S1, S2, S3, S4. So give me from S to all destinations. All right. And the idea here is the output of this algorithm is going to be a table. Okay. So if S itself is the destination, then the cost will be 0. Going from S to S is going to be 0. And the path is going to be simply the empty path. If I want to go from S1, cost is 1, path is going to be S to S1. If I want to go to S2, cost is 2.5, S to S1 to S2. So I want to build up like this. Okay, so I mean for every possible destination, I want to know what the shortest path cost is, and I also want to retrieve the path for you. All right, so and this is called single source. And so if you want to know the shortest cost path from S to T, then you look it up from the table. Source node S. So build a single source shortest path table from S and look up the cost of S to T. And this allows you to go from S to T. If you change your mind, you can go from S to T2, S to T3. But if you change the source in this table, you will have to recompute a new table for the new source potentially. And this is called single source. The other kind of problems are called all pairs. Here, I want to compute for all pairs of vertices. For all pairs of vertices, I want to compute the shortest path distance. And I want to compute the shortest path itself. Okay. Now, obviously, this is going to be more expensive than what? Than single source, right? It's going to be way more expensive than single source, but we will look at it next week. All right. So this week we are going to look at single source. All right. Very good. Now, one of the important things is, what about single destination? Does that even make sense? So suppose I have a destination T, and for every possible source, I want to know the shortest path from that source to the destination. So for example, suppose T is Rome, knowing that all roads lead to it, it's a natural question to know what's the length of the shortest path to Rome. All right. But interestingly enough, if you know how to solve single source, you can easily solve single destination. How is that? Well, take your graph, just reverse the direction of all the edges, compute the transpose graph or the reverse graph, and simply solve a single source shortest path problem on this transpose graph, and you're done. Right? So single destination is easy if you know how to solve single source. So we will mostly focus on solving single source shortest path problems. All right, so now I'm going to talk more about single source shortest path problems. Okay, so in a single source shortest path problem, I have as an input a weighted directed graph G with vertices V. So number of vertices is N, edges E, number of edges is M. All right, and there is a weight function. So if you have an edge from U to V, there is a weight on this edge. Okay, the weight can be positive, the weight can be negative. Sometimes you can have negative weights. What's the meaning of negative weights? Depends on the problem. Of course, if weights are measuring distances, then negative weights are not going to be meaningful. On the other hand, if weights are measuring the difference between the length of the road and 2 kilometers, let's say. So if the road is less than 2 kilometers, maybe I put in a negative value for some reason, and then let's say that's the way my problem's built. So then negative weights have a meaning there, right? All right, so very good. So and sometimes, for example, let's say a company has built a brand new road, and it's incentivizing you to take that road by giving you $10 every time you take the road, and that offer is valid until October. Okay, just to get people on this new road. All right, well, in that case, there is an incentive given to you to take the road, and therefore you might have negative weight edges in such a graph. If you're a logistics company and you want to represent this incentive, you might do so with a negative weight edge, because, well, every time you take that edge, you're going to gain some money, so that's a negative cost. All right, so these are the inputs to the problem. Now it makes sense to think carefully about the outputs, and I've already told you what the output looks like. Well, the output looks like this. So I need a table. And so for every destination, S, S1, S2, blah, 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 I need a cost, a distance, the shortest path distance to that destination. And previously I told you I need the path itself. What's the shortest path? What are the sequence of edges I need to traverse to get from S to S1? So S to somewhere else, to somewhere else, to somewhere else, to S1. All right. Now I need a sequence of edges to traverse. All right. How do I represent that? Well, I'm going to talk about this right now. So first property of shortest paths is shortest paths form a tree. All right, so let me do that with an example, with a concrete example, and then explain what I mean and prove the property. So first property is shortest paths form a tree-like structure. What does that mean? So let's take an example. So here is a graph. Okay, so here's your graph, And I would like to have a source vertex of 1. And I would like to know the shortest path from the vertex 1 to every other vertex in the graph. All right, so the result is going to be a table. So source is 1. And what are the destinations? The destinations are, okay, so I build a table for various destinations. So destination could be 1, the source itself, 2, 3, 4, 5, and 6. All right, so what's the cost of going from 1 to 1? That's the easiest part, 0. And the path is empty. So I'm going to write epsilon for empty. All right, so that's going to be the simplest thing. What about 1 to 2? Well, this is easy. You can work it out. The shortest path from 1 to 2 cost is 1, and the path is go from 1 to 2 directly. What about from 1 to 3? Well, if you look at it, there's many ways of getting from 1 to 3. So I could go from 1 to 2, 2 to 3. The cost of that is 3. I could go from 1 to 4, 4 to 3. Cost of that is 4.5. 1 to 2, 2 to 4, 4 to 3, and there's multiple ways, but if you see this, the shortest path is going to go from 1 to 2. For destination 3, the shortest path cost is 3, and it's going to go from 1 to 2, 2 to 3. For destination 4, the shortest path is going to go from the cost is going to be what? 1.5. Okay, and it's going to go from 1 to 4. Okay, for destination 5, it's going to go from what's going to be the cost. Okay, the cost is going to be 4. Okay, and it's going to go from 1 to 2, 2 to 3, 3 to 5, and for destination 6, the cost is going to be 3, and it's going to go from 1 to 4, 4 to 6. All right. Okay, so now one thing to notice is that the path is going to be difficult to store. So what can we do instead of storing this path? So one thing to do is we can always record the parent pi. So the parent is going to be the last node before the destination node. So for example, if you're going from, so the parent for 5 is going to be 3, and the parent for 6 is going to be 4. Okay, and this is always the last but one node before you reach the destination node, as I have shown by circling. All right, now if I just store this last but one node, it's enough. And remember, if we've already seen this in BFS and DFS, it's the concept of the parent pointer pi, right? And by storing the last but one node, it's easy to see. So if t hat is the last but one node, then if I need to get from s to t hat, right? So if it's the last but one, if I need to get from s to t hat, then if I know how to get from s to t hat, then I know how to get from s to t. Okay, and that's the important part. So this is an important aspect of shortest path. I don't need to store the entire path. I just need to store the last but one node, and I can recursively recover the path. Is that okay? All right, so this is an important part. Okay, and we already saw some of this in breadth first search. All right, now this gives us a property of shortest path. If I know commit to reaching t hat and reaching t through t hat, then if I get the shortest path from s to t, it must contain the shortest path from s to t hat, right? The shortest path from s to t must involve shortest path involves shortest path from s to t hat. All right, and this is important. Okay, and this is a form of something that you have seen before, and this is nothing but a statement of the optimal substructure property stated in the reverse direction. Okay, and that's important to know. So why is this the case? Let's take some other path, yellow path from s to t hat, and let's say if that were shorter than the red path from s to t hat. Well, by concatenating the yellow path and the red edge from t hat to t, I could have gotten to t in a shorter manner. Okay, and so this is just a form of the optimal substructure property. And that's in the reverse manner. So this is the optimal substructure in the reverse direction. There is another way of stating the optimal substructure. Suppose I start from S and I commit to going to a node S hat. Okay, then if I want to get the shortest path from S to T, then this segment must also be the shortest path from S to T hat, and that's important to note. So here this is the optimal substructure in the reverse sense. If I know that the last node before T hat T is T hat, then I need to get to the shortest path from S to T hat. Likewise, if the first edge from S is to S hat, then the segment from S hat to T must be the shortest path. Okay, so this is an instance of optimal substructure. And so, like you guess, shortest path algorithms are going to be a form of dynamic programming on graphs. Okay, and this cost table that you see here is going to be like your memo table. Okay, and you don't need to store the paths, you just need to know how the parents so that you can look up. So the parents are giving us the option for T hat that's giving us the shortest path overall from S to T. All right, so once we know this, how do we look up the answer? Well, if you know the parent, and suppose you want to look up the path from 5, well, the parent of 5 is 3. So I know that the last edge on the path is 3 to 5. What's the parent of 3? Is 2. So I know that the edge to get to 3 must be to 2. What's the parent of 2? 1. So, but 1 is the source. So to get to 5, I need to go 1 to 2 to 3 to 5. Okay, so this is important. All shortest path algorithms are going to build a cost table and a parent table. All right, and this is going to be important, and hopefully this is clear why we need to build both. Okay. Finally, we will talk about the effect of cycles. So far, we have not really talked about cycles. What do cycles end up doing to the shortest path problem? So here's an example of a graph. Okay, so I'm going to draw a graph. All right. And the edge weights are 2, 3, 1, 4. Okay. So does this cycle matter? Well, the problem with a cycle is it gives you infinitely many paths from 1 to 4. So you can take from 1 to 2, 2 to 3. You can take from 1 to 2, 2 to 5, 5 to 4, 4 to 2, 2 to 3. And this takes a cycle once. Now you can cycle twice. So you have infinitely many possibilities in the graph, right? But the nice thing is, because the weight of the cycle is positive or is greater than or equal to 0, okay, even if it were a 0 weight cycle, this would be true. The cycle doesn't matter. Taking the cycle only makes the paths costlier. Good. Unfortunately, if your graph has negative weights, this is no longer true. So let's take the same example, but let's make negative weights now. Now the weight of the cycle here is -1. So this is a negative weight cycle. So going around this cycle, so the shortest path distance from 1 to 2, 2 to 3 is -infinity. Why is that? Because I can keep going around the cycle and I can make the weights of the path smaller and smaller and smaller. So if a graph has a negative weight cycle, then shortest path distances from any source to any destination is taken to be either you can take it to be undefined or negative infinity. And I will explain why we go for such a drastic interpretation, negative infinity. All right. Now here's the idea. So suppose I have a graph. Okay, let's go back to this original graph, which is already a nice graph. And let me add a new edge from a new node 1 to 5. 1 to 5. And let's give it a weight 2. So you might say, well, hey, 1 to 2 is well defined, is not well defined because the negative cycle comes into effect. 1 to 3 is not well defined. 1 to 4 is not well defined. 1 to 5 is not well defined. But there is a shortest path from 1 to 5, which is 2, right? That is one interpretation. However, remember that this negative weight cycle has this following interpretation too. So if an edge doesn't exist in the graph, let's say 5 to 1 doesn't exist, you can say it exists with cost infinity. This is one of the interpretations you can give. Okay, it's one interpretation. And this we will use it again and again in certain problems. So you assume that there is a plus infinity weight edge from 5 to 1, from 4 to 3. So under this interpretation, you see, if you have a negative weight cycle, that's going to mess up the distance to 5 because now you are being forced to add minus infinity to plus infinity and the answers are undefined. In the worst case, so it's not ideal to talk about shortest paths when you have negative weight edges. Okay, and I call it the the foreign taxi problem. This is very common if you have taken taxis in foreign capitals where you're completely unaware of what's going on, right? And the taxi driver can sometimes take you through a really circuitous path for a long time to your destination, charging you up a lot of money. And this has happened to be in a couple of foreign capitals where I did not know the place well enough. All right, I won't name names, but this has happened to me, and I call it the foreign taxi problem. So even though you may not be on the path to your destination, you may still end up being charged a lot of money. And negative weight cycles have that kind of a flavor. Even though this negative weight cycle does not impact 5, you may interpret an infinite weight edge from 5 to 1, a plus infinity weight edge, and now you are being forced to add minus infinity and plus infinity, which either gives you undefined result or gives you a really bad answer. In any case, this is not ideal. So we generally don't answer this question if your graph has a negative weight cycle. Okay, so that is more of what by an introduction to shortest paths. In the next lecture, I'm going to talk about the first algorithm, which is the dynamic programming algorithm. And it's called the Bellman-Ford algorithm. It's a simple algorithm. It's going to set up shortest paths as a dynamic programming problem and solve it. And hopefully it will be an introduction to dynamic programming on graphs for you. All right. See you in the next lecture. Bye.